We've been on a journey through the transport layer, looking at TCP, UDP, and what makes them the same and what makes them different. It's now time for the last mile of this journey as we look at error recovery and windowing. Data can be lost for so many reasons. These errors are generally detected by the data link protocol, like Ethernet, which will drop bad frames. Both TCP and UDP have some error handling built in. They can detect corruption by using the value in the checksum field, but only TCP is considered reliable. This is because it will manage retransmission of the lost data. UDP, on the other hand, is considered unreliable, as it will not try to recover from data loss. To understand how this works, we must first look at how the segments are acknowledged. You'll remember that when a segment is received, the receiver sends an acknowledgement message confirming that it got the data. In the last video, we saw that there are sequence numbers in the TCP header. One function of this is to reassemble the segments into the correct order, but they also affect acknowledgements. Think of the three-way handshake. Let's say that the sequence number was initialized to 97, and that was sent in the SYN message. The SYN ACK message would use a sequence of 98, and the final ACK would be 99. After the handshake is complete, the meaning of this sequence number changes. It won't count the number of segments sent back and forth anymore. Instead, now it will count the number of bytes that have been sent. The first segment that carries data then would have a sequence number of 100, as it's the next sequence number. Let's now say that this segment is 100 bytes long. The server will get this segment and will need to send back an acknowledgement. It doesn't just send the ACK flag though, it also uses the acknowledgement field. It will set this value to 200. Why? Because it's using a process called forward acknowledgement, where it's acknowledging the data that has been sent and telling the sender what it's expecting to get next. So why 200? We started with a sequence number of 100. We sent 100 bytes, and now we're ready for the data starting at byte number 200. When the next segment is sent, the sequence number is set to 200. Do you see how the sequence numbers track not the number of segments, but the number of bytes being transferred? The advantage to this is if data went missing, there would be no acknowledgement for that range of bytes. The sender could then resend that range of data. But it's not very efficient to send an acknowledgement for every single segment. The sender would need to stop sending and wait for the ACK message before sending the next segment. The receiver would also need to spend more compute power generating these messages. So, to make it more efficient, TCP uses a process called windowing. This allows the sender to send a certain amount of data, usually over multiple segments, and the receiver can send one single acknowledgement to cover all of them. The amount of data that can be acknowledged in a single message is called the window size. This value is stored in the window field of the TCP header. Imagine that the window size is 1000 bytes. In the real world it would be much larger, but we're just using simple numbers for the example. The sender now sends a segment with 100 bytes of data. The window size shrinks by 100 bytes to 900 bytes. There's no need to send an acknowledgement back yet, as there is still room in the window. The sender sends 9 more 100 byte segments. The window shrinks by 100 bytes each time, and when the window reaches 0, the sender will stop and wait until it receives an acknowledgement. Once acknowledged, the window size resets back to 1000 bytes. In the real world, the receiver will not wait for the window to shrink to 0 before sending an acknowledgement. This is so the sender does not have to stop and wait for the acknowledgement, which is better for traffic flow. Now time for a quick quiz. Do you remember what out-of-order delivery is? How does TCP handle this situation? After the three-way handshake completes, the meaning of the sequence field changes. What does it mean now? And how is it used? Now we've covered that, we can look at error recovery. Think of the example once again. Now imagine that there's a problem somewhere, and the fourth segment does not arrive. It's time for error recovery to kick in. The server has received 9 segments, but bytes 400 to 499 are missing. It knows this because the third segment starts at byte 300, it is 100 bytes long, so the next segment should start at 400. But, after waiting a reasonable amount of time, it still does not have the segment starting at byte 400. But the server can still acknowledge the data that it has received. It can send back an ACK message with 400 as the acknowledgement number. This is saying that it expects data starting at byte 400 next. This is a really simple method of error control. It's not completely efficient, as every frame from byte 400 is resent. And this is just one way that error control can work. There are other methods. One example is selective acknowledgement, or SAC, which doesn't need to resend all the segments. Right now though, the important thing is not to learn all the error control messages, but to remember that TCP uses error recovery and UDP does not. If errors are becoming frequent, TCP can adapt with a type of flow control. What it will do is dynamically change the window size. We've seen that the three-way handshake initializes values like port numbers, the ISN, and the window size. We've also seen that the window size is the amount of data a device can send before requiring an acknowledgement. So, the three-way handshake is where they agree on the initial window size. But the window size isn't just set between two devices. It's set for each connection, and each connection can have a different size. Each connection can change over time too, which is why it's often called a sliding window or a dynamic window. Okay, that's nice and all, but what's the point? The point is that the receiver can tell the sender to send more information or less information per acknowledgement. Let's think about when a connection first starts. The devices at either end do not know how reliable the network path really is. Hopefully it's a rock-solid reliable connection that rarely drops any data at all. But it could also be a very flaky connection that regularly drops data. To deal with this, they may start with a relatively small window size, let's say 8 kilobytes. Remember that this means the sender can send up to 8 kilobytes of data before the receiver needs to acknowledge it. Now, if this goes well, that is to say, if this is a reliable connection with very little or no data loss, they may decide to increase their maximum window size. Maybe they'll put it up to 16 kilobytes. If it continues to go well, they may take it to 32, and then 64. The original TCP protocol would consider 64 to be the largest window size, but newer implementations can go even higher than that. On the other hand, what if the connection was losing data? A large window size would not be good here. Remember that error control in some TCP implementations will resend everything from the point where data was lost? A large window would mean that there's a lot of unnecessary retransmissions. So instead, the window will shrink. Data is acknowledged more often, and hopefully, there are fewer retransmissions. A receiver could also use windows to signal the sender that it's overwhelmed. It could set the window size to 0, which would effectively pause the sender, giving the receiver time to catch up. Obviously, that's not ideal, and it's a symptom of a much larger problem. Here's an opportunity to see if you really understand what we've been talking about. Even if you don't want to use my answers, try to use these questions to challenge your understanding. We've seen a lot of TCP and UDP over the last few videos. This will be enough for the exam, but only really scratches the surface of what these protocols can do. Next in this series, we'll move from theory to practical and look at the very basics of configuring a Cisco router or switch. If you thought this video was good, hit the like button and share it. And I'll see you all soon.